Hello and welcome to the lecture on 10.6. Today we're going to talk about determinants. Now a determinant is just going to be a number that we assign to a matrix. It's like an operation that we perform in order to get this number. If a matrix is square, then we can assign to it a number called its determinant. Now I do need to note, determinants only exist for square matrices. Now remember what a square matrix is. It has the same number of rows and columns. The determinants for non-square matrices do not exist. Determinant of a 2x2 matrix. So there's a certain process that we do in order to find the determinant of a 2x2. We'll also use this process when we're looking for determinants of higher order matrices, n by n, but we need to start at the 2x2. The determinant of the 2x2 matrix A, B, C, D is determinant of A equals, now sometimes we use this notation with the absolute value of A. It just means determinant when A is a matrix, which is equal to the determinant of A, B, C, D, which is just rewriting the matrix A in this form, which is going to be A times D minus B times C. So what we do is we take our entry A, multiply it by our entry D, and then subtract the product of entry B and C. Right. That's how you find the determinant of a 2x2. It's pretty straightforward, but let's go ahead and do an example. Find the determinant of A, which is equal to 2, -1, -6, 3. Now generally I'm going to write it in this notation, but occasionally I will write det of A, this, because the determinant is sort of like a function. We're using entries in A to find a value, but generally we write it with the absolute value bars instead. So the determinant of A is going to be our entry A11 times entry A22, subtract entry A21 times entry A12. So we do 2 times 3 minus -6 times -1. So we have 6 minus 6, which is 0. So the determinant of matrix A is 0. Now this is significant, and we'll learn about this in a bit here. But first, let's go ahead and get into the determinant of an n by n matrix. When taking the determinant of an n by n matrix, we need to figure out a couple of things, namely the minors and cofactors. Let's figure out what these are first, because we need these in order to find the determinant of an n by n matrix, basically an arbitrarily large square matrix. Let A be an n by n matrix. 1. The minor m sub ij of the element A sub ij is the determinant of the matrix obtained by deleting the ith row and jth column of A. So I want you to notice a couple of things here first. M sub ij, ith row, jth column. So we're deleting the ith row and the jth column of A, and then we're finding the determinant of the remaining matrix. Now, I also want to note that since we're deleting the ith row and jth column, we have an n-1 by n-1 matrix that we're taking the determinant of. Specifically that our square matrix is 1 row and 1 column smaller. So we can continually do this in a recursive fashion, and eventually we'll get down to a 2x2 matrix, which we already know how to find the determinant of. So if we continue in the fashion of deleting an ith row and jth column, and you'll see how that works as we get into some of the examples, then eventually we'll get to a 2x2, which we know how to take the determinant of, and then we can just move on from there. 2. The cofactor A sub ij of the element A sub ij is aij is equal to negative 1 to the I plus j times the minor m sub ij. Now here, we're just tacking on the cofactor, we're just tacking on a negative 1 to the I plus jth power. Now this is important when we move through when we do the determinant. This is very important. You need to make sure that you have the correct sign on your minor. So here, the I plus j is the power on negative 1. So either we're going to have a positive 1 or a negative 1, depending on the position of ij. So if one of the positions is odd and one of the positions is even, then we have a negative 1. If both are odd or both are even, then we have a positive 1 for our minor. All right, let's go ahead and do an example on how to find the cofactor and the minor of a n by n matrix. Let A equal 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's suppose that we have this matrix A. Now what I want to do is I want to find m sub 1, 2 and m sub 3, 1. Then after we figure out those two, we're going to find a sub 1, 2 and a sub 3, 1. Let's go ahead and find our minors first. Now for a 3 by 3 matrix, it'll be pretty easy to find the minors, because when we delete a row in a column, we're going to end up with a 2 by 2 matrix. I'll show you what I mean here. So m sub 1, 2. We find the minor m sub 1, 2 by deleting the ith row and jth column. In our case, I is 1, j is 2. So we delete the first row and second column. So the minor will be the determinant of the remaining matrix. So the remaining matrix is 4, 6, 7, 9. I'm going to go ahead and undo these two red lines. Our minor is going to be that we're finding the determinant of the matrix 6, 4, 7, 9. Now we know how to find the determinant of a 2 by 2, so we do 4 times 9 minus 7 times 6. 4 times 9 minus 7 times 6. 4 times 9 is 36. 7 times 6 is 42. So we have a negative 6 as our minor. Our minor m sub 3, 1 will be done in exactly the same way, except now we delete the third row and first column. So we delete the third row and first column. We look at the remaining matrix, 2, 3, 5, 6. So this matrix, this 2 by 2 matrix, is what we're taking the determinant of in order to find the minor m sub 3, 1. So 2, 3, 5, 6. Now again, we know how to take the determinant of a 2 by 2. So we do 2 times 6 minus 5 times 3. 2 times 6 is 12. 2 times 6 is 12. 5 times 3 is 15. So we get a negative 3. Now we need to determine what the cofactor a sub 1, 2 is and the cofactor a sub 3, 1. Let's start with 1, 2. Now remember, the cofactor is going to be negative 1 to the I plus j. In our case, I is 1 and j is 2. So we have negative 1 to the 1 plus 2 times the minor m sub 1, 2. So we have negative 1 to the 1 plus 2 times m sub 1 plus 2. Now negative 1 to the 3 power is negative 1. So we have negative 1 times this minor. Now remember, the minor is negative 6. We already found that. We do a negative 6 here, and we get 6 as our cofactor. Now a sub 3, 1, when we look for this, so we do the exact same thing. In this case, though, our I is 3 and our j is 1. So we do negative 1 to the 3 plus 1 times the minor m sub 3, 1. Now m sub 3, 1 is negative 3, so we have a negative 1 to the 4th power times negative 3, which will just give us negative 3. Because negative 1 to the 4th power is positive, so we just multiply 1 times negative 3, we get negative 3. All right, we're finally ready to take the determinant of a square matrix. If A is an n by n matrix, then the determinant of A is obtained by multiplying each element of the first row by its cofactor and adding the results. Symbolically, it is as follows. Determinant of A equal to, we use A in absolute value bars, which again is the determinant of A, which would be the absolute value of A sub 1, 1, A sub 1, 2, all the way up to A sub 1, n, A sub 2, 1, all the way up to A sub 2, n, and we do this repeated all the way down to A sub n1 up to A sub nn. Now, we generally choose the first row, which is equal to A sub 1, 1, A sub 1, 1, plus A sub 1, 2, A sub 1, 2, all the way up to A sub 1, n, A sub 1, n here, like this. Now, I do want to note that we generally use the first row, and that's how we teach it in the book, but it's not necessary. You don't necessarily need to use just the first row. You can use any row, or you can use any column for that matter. The determinant can be found using any row or column. Now, again, what I mean by this is that we don't necessarily have to use the first row, as stated here in how we find the determinant of a square matrix. You can use any row or any column. It does not matter what you use, as long as you get the correct cofactors. Now, I will recommend that you use the first row, at least until you get the determinant down. Now, notice up here, when we did these cofactors, you have this negative 1 to some power. When we use the first row, those negatives will always be in the same spot. So you can get used to using the first row and having the negative where you want it consistently. And that's why I recommend that you use the first row until you feel comfortable using a different row. Now again, if you use a different row, then you would need to calculate the cofactors accordingly. Now in my example here, I'm actually going to find the determinant in multiple ways. So if our matrix is A is equal to 1, 2, 5, negative 2, negative 3, 2, 3, 5, 3. I'm going to find the determinant using the first row first, and then I'll use the second row, and then I'll use one of the columns. So remember, when we're using the first row, if we go back to our determinant of a square matrix, it's obtained by multiplying each element of the first row with its corresponding cofactor. So we take our first row, and I'm just going to leave this crossed out. And each element in the first row is going to be multiplied by its corresponding cofactor. So A11, A11, plus A12, A12, plus A13, A13. Right? Now the cofactors, the first one will be positive, the second one will be negative, and the third one will be positive. In terms of this negative 1 that's added at the front of the cofactor. Remember, we have the negative 1 to the I plus j. Here, I plus j will be even. Here, I plus j will be odd. And here, I plus j will be even again. So we would have plus, minus, plus for our negative 1 value. I'm going to do them all individually first, and then in future examples of finding determinants, I'm not going to do that anymore. We'll just use the plus, negative, plus. Hopefully you'll see what I mean here in a second. So A11 is 1. Now capital A11 is equal to -1 to the 1 plus 1, which is positive 1, times M11. Now remember what M11 is. We cross out the first row, first column, because that's I and J, and we take the determinant of the remaining matrix, so -3, 2, 5, 3. So M11 will equal the determinant of -3, 2, 5, 3, like this. -3 times 3 is 9, minus 5 times 2 is 10. We have -3 times 3, going to be -9, minus 5 times 2, which is 10. So -9 minus 10 is -19. So a sub 1, 1 will be -1 to the second power times -19. A sub 1, 2. Now here, again, we do -1 to the I plus j power, so it'll be 1 plus 2 here, m sub 1, 2. Now here, m sub 1, 2 will be crossing out the first row and the second column, and taking the determinant of the remaining matrix. We cross out the first row, cross out the second column, and the remaining matrix will be -2, 2, 3, 3. We do the determinant of -2, 2, 3, 3. -2 times 3 is -6. Minus 3 times 2 is 6. We have this. We have -2 times 3 is -6, minus 6 is -12. So -1 to the 1 plus 2 power to the third power times -12. This will be a -12, which is positive 12. And then we need to find a sub 1, 3. This will be -1 to the 1 plus 3 power. Now that's an even power, so this is just going to be a positive 1, times m sub 1, 3. Now m sub 1, 3 will equal the determinant of the matrix remaining after crossing out the first row and third column. The remaining matrix here will be -2, -3, 3, 5. So we have -2, -3, 3, 5. That will be -2 times 5, which is going to be 10, -10, and not 3 times -3, which is going to be a -9. So we have -10 plus 9, which is -1. We end up with -1 to the fourth power, which is positive 1, times -1. So I found all of my cofactors for the first row. Now we need to multiply those by the corresponding elements. So A11, A11. So A11 here is the element 1. First row, first column of the matrix, element is 1. Multiply that by -19, plus A sub 1, 2. First row, second column, that element is 2. Times A sub 1, 2, which is 12. Plus A sub 1, 3, which is 5. First row, third column, 5. Multiply that by the cofactor A sub 1, 3, which is -1. So we have 5 times a -1. And then we add all of these results. -19 plus 24 minus 5. -19 plus 24 is 5. 5 minus 5 is 0. So we end up with 0. So now let's do this with the second row. Now, As I said before, you can use any row or any column. That means that we should get the same answer. So a sub 2, 1 times the cofactor a sub 2, 1 plus a sub 2, 2 times the cofactor a sub 2, 2 plus a sub 2, 3 times the cofactor a sub 2, 3. None of these are what we need, so we need to figure out each of the cofactors, and then we'll use the entries times the corresponding cofactors. So we need the cofactor a sub 2, 1. So now what we're doing is crossing out the second row and first column. And the remaining matrix will be 2, 5, 5, 3. So this will be negative 1 to the 2 plus 1 power, which is 3, so this will be a negative 1, times the determinant of the matrix 2, 5, 5, 3. Because we're crossing out the second row, first column. So the remaining entries are 2, 5, 5, 3. Now the determinant of 2, 5, 5, 3, this will be a negative 1 times 2 times 3 is 6, minus 5 times 5, which is 25. So 6 minus 25. A sub 2, 2 would equal negative 1 to the 2 plus 2 power times the matrix times the minor m sub 2, 2, which will be obtained by crossing out by deleting the second column and second row. Remember, when we look for a minor, we're deleting a row and a column. We delete the second row, second column. The remaining matrix is 1, 5, 3, 3. So we're looking for the determinant of 1, 5, 3, 3. Now, negative 1 to the 2 plus 2 power is just a positive 1. So we have 1 times 3 is 3, minus 3 times 5 is 15. We get a negative 12. Up here we have, this would be negative 19 times a negative 1 is a positive 19. And last, we have a sub 2, 3. The cofactor a sub 2, 3 will be negative 1 to the 2 plus 3 power times the determinant of the matrix obtained by deleting the second row, third column. So we delete the second row and third column. That means the remaining matrix is 1, 2, 3, 5. 1, 2, 3, 5. So we'd find the determinant of this matrix. We would have negative 1 to the 5th power times 1 times 5 is 5, minus 3 times 2 is 6. So we have 5 minus 6. Negative 1 times negative 1 is a positive 1. So a sub 2, 3 is 1, a sub 2, 2, negative 12, a sub 2, 1 is 19. Now remember how we find the determinant of this matrix. A sub 2, 1 times the cofactor a sub 2, 1 plus a sub 2, 2 times the cofactor a sub 2, 2 plus a sub 2, 3 times the cofactor a sub 2, 3. So a sub 2, 1 will be negative 2 times the cofactor a sub 2, 1, which is 19, plus a sub 2, 2, which is negative 3, times the cofactor a sub 2, 2, which is negative 12, plus a sub 2, 3, which is going to be 2, times the cofactor a sub 2, 3, which is 1. So here this is negative 38 plus 36 plus 2. Negative 38 plus 36 is negative 2. Negative 2 plus 2 is 0. Let's do it one more time. But let's do it with a column now. And I'm just going to choose the first column. We already have 2 out of the 3 cofactors for this one. So I'm just going to repeat those. Remember, if we use the first column, it's again the entry times the cofactor in the first column this time. So a11 times the cofactor a sub 11 plus a sub 21 times the cofactor a sub 21 plus a sub 31 times the cofactor a sub 31. Now the only one I really need to find is the cofactor a sub 31 because I already have the cofactor a sub 21 right here and the cofactor a sub 11 right here. So a sub 31 will equal negative 1 to the 3 plus 1 power, which will be a positive 1, times the determinant of the matrix obtained by finding the remaining elements after deleting the third row, first column. So we delete the third row, first column. The remaining matrix is 2, 5, negative 3, 2. We delete the third row, first column. So 2, 5, negative 3, 2. And we find this determinant. And the determinant of that will be 2 times 2 is 4 minus negative 3 times 5, which is 15. So 4 minus negative 15 will be a 19. And then we have obviously a negative 1 to the 4th power as a positive 1. So this will be a sub 31. Now we do a sub 11 times the cofactor a sub 11. We would have 1, which is a sub 11, times the cofactor a11, which is negative 19, plus a sub 21, which is negative 2, times the cofactor a sub 21, 19, plus a sub 31, 3, times the cofactor a sub 31, which is 19. This actually is really nice. A negative 19 plus 2 negative 19s plus 3 19s. This is going to obviously be 0 because I have 3 of this object here. I have negative 2 of this same object here. And if you switch the negative, you have a negative 1 of this object. So negative 1 plus a negative 2 of the same object gives us a negative 3 of that object. Negative 3 of that object plus 3 of that object will give us 0 of that object, which will just be 0. Now, as I stated before on the previous example, having a 0 for a determinant is significant. We're going to talk about the invertibility criterion just for a second. If A is a square matrix, then A has an inverse if and only if the determinant of A is non-zero. Now, in the previous two examples that we did, we had a 0 determinant. That means that these matrices are not invertible. Remember, matrices can be invertible if they're square. They don't all have inverses, but those are the only types of matrices that actually do have inverses are square matrices. If we have a square matrix, and it so happens that our determinant is equal to 0, then that matrix is not invertible. Because a matrix has an inverse if and only if the determinant is non-zero. Try one on the accompanying worksheet. Find the determinant of A, then determine if A is invertible, where A is equal to 2, 1, 0, 0, negative 2, 4, 0, 1, negative 3. All right, the next thing I want to talk about is going to be rows and column transformations. Recall, there are 3 operations that we can do to a matrix that will not change the solution to a system of equations. This doesn't exactly apply because when we have a matrix that is an augmented matrix that is a system of equations, remember we have one more column than rows. Because we need a column for the solutions to the system. But there are 3 things that we can do to a system of equations That doesn't change the solution set, meaning that we would get an equivalent system. Now, those three things are add a non-zero multiple of one row to another, multiply a row by a non-zero number, and swap two rows. Now, these three things do not affect a system of equations. They'll give you the same exact solution, but these three things do affect a determinant. And that should make sense. If we swap two rows, then our cofactors might be off by some negative value because the I plus j in the exponent of our cofactor changes. So swapping two rows might affect this. So what I'm going to do is I'm going to show you the three things that happen when we use these modifications on matrices. If A is a square matrix, and if matrix B is obtained from A by adding a non-zero multiple of one row to another or one column to another, then the determinant of A is equal to the determinant of B. Now, what I'm saying here is that if we add a non-zero multiple of one row to another in a matrix, it doesn't change the determinant, which is kind of interesting. Interchanging two rows, then the determinant of A is equal to the negative of determinant B. Multiplying a row by a non-zero scalar C, then the determinant of A is equal to 1 divided by C of determinant B. So, these are actually pretty interesting. The first one doesn't do anything, which is very fascinating. The second one sort of makes sense because when we take our exponents, if we swap two rows, our exponents change. So we're getting negatives where we normally wouldn't have negatives and positives where we normally wouldn't have positives for a particular row, for two particular rows. And then multiplying a row by a non-zero scalar C, this one should make sense. If we take a row and multiply it by C, then we need to offset that C in the determinant because each element here, a something something, a something something, and a something something, will be multiplied by C. Now we only need to multiply one row by C in order to get our determinant to need to offset by 1 over C. Now if we multiplied all of the rows, then we would have 1 divided by C to the n power. However, where n is the size of the matrix. Now personally, I don't think we need an example of these. These are interesting, not really that necessary because we can always find the determinant anyway, and comparing them is kind of beside the point. It's just helpful when you know them, you can immediately find the determinant of another matrix when you've changed that matrix by something small. Next topic I want to talk about is areas of triangles using determinants. If a triangle in the coordinate plane has vertices a1, b1, a2, b2, and a3, b3, then its area is a equals plus or minus 1/2 times the determinant of a1, b1, 1, a2, b2, 1, and a3, b3, 1. Where the sign is chosen to make the result positive. So here, what we're saying is if we have a triangle in 2 dimensions, so we have 3 vertices, and our triangle looks like this, where we have a1, b1, a2, b2, and a3, b3, then we can find the area of this very easily by just finding the determinant of this matrix and dividing by 2. Also, again, you have to add the sign, make sure that your sign is positive. If your determinant comes out to be negative, just make it positive. That's what that means that's what this means, this plus or minus. Let's do an example of this. Find the area of the triangle with vertices 1, 0, 3, 5, and -2, 2. So as I stated before, we would just have the area is equal to plus or minus 1/2 times the determinant of the matrix 1, 0, 1, 3, 5, 1, negative 2, 2, 1. This last column is always ones. It's just how it is. So here, if we do the determinant, I'm going to just do the top row. And how I normally do the determinant is not by finding each of the cofactors. That's a very long way to do it. So I cross out the first row, cross out the first column, and I see the element that's crossed out twice. I write that element times the determinant of the remaining uncrossed out values. So here it will be 1 times the determinant of 5, 1, 2, 1. Now we need to add a negative only on the middle term when we're doing the first row. Because here, remember, it's 1, 1. The position is 1, 1. So it would be normally negative 1 to the 1 plus 1. This one would be negative 1 to the 1 plus 2, which is odd. And then the third one is negative 1 to the 1 plus 3, which is even. So this first one, our cofactor will be positive. The second one, our cofactor will be negative. And the third one, the cofactor will be positive. So I need to account for that. And I account for that with a single negative. I'll show you and explain it when I place it. So here, we're going to do 1 times the determinant of this matrix. So we have 1 times the determinant of 5, 1, 2, 1. It's like this. Now we subtract the second term because of that negative 1 to the 1 plus 2 power. The negative 1 to the 1 plus 2 power in the cofactor, a sub 2, 1, will be negative. That's where this negative is coming from. So it's always the first one minus the second one plus the third one, if you're using the first row. Now we cross out the second column, and the remaining matrix is 3, 1, negative 2, 1, and the term that's crossed out twice is 0. So we'd end up with 0 times the determinant of the matrix 3, 1, negative 2, 1. And then again, plus the third element, and we cross out the third column here. So the remaining matrix will be 3, 5, negative 2, 2, and the element that's crossed out twice is 1. So it'll be 1, because 1 is crossed out twice, times the determinant of 3, 5, negative 2, 2. We have this. 5 times 1 minus 2 times 1 is just going to be 3, so we have 1 times 3. Minus 0. I'm not even going to take the determinant because I don't need to. It's going to be multiplied by 0. And then 3 times 2 is 6 minus a negative 10. So this will be 1 times 6 minus negative 10 is 16. Don't forget your plus or minus 1/2 out front. We have 3 minus 0 plus 16 is plus or minus 19 over 2. Now remember, we choose the positive or negative just to make this entire term positive. If it was negative 19 over 2, then I would choose the negative to make the area positive. But since 19 over 2 is already positive, I'm just going to choose the positive and ignore the negative. So our answer is 19 over 2. All right, that's going to be it for today. I will see you all in the next lecture.